Okay, so what I want to do today is to give Iwasawa's proof of theorem B. So remember that, well, let me remind you of the situation. We have an arbitrary finite extension f of q, and we have the cyclotomic ZP extension, which we're actually assuming there are enough roots of unity in the ground field that this ZP extension f infinity is just f adjoin mu p infinity. And as usual, I'm writing gamma for the Galois group of f infinity over f. And En prime will be the p units of Fn. So they're the units when you, the set of, you allow, I mean, you take the ring of integers localized at the primes, the p integers and take the units of that ring. And this curly En prime is simply you divide En prime by the roots, the appropriate torsion subgroup. So it's, and we actually proved last time that even for n equals infinity, for n finite, of course, that's obviously a free abelian group, but even for n equals infinity, it is a free abelian group. And let me remind you what we want to prove, of course, is that the field that you get by adjoining to f infinity the p power roots of all of these units in E infinity prime, that Galois group, we're going to, in effect, completely determinate of that extension, and in particular show that its rank is R2. And I'm following very closely Iwasawa's proof in his paper. So now I want to write Q prime for the ring of rational numbers whose denominator is a power of P. So in other words, the localization of Z at the prime ideal P. And then it's obvious, as I've remarked here, that Q prime modulo Z is the same as QP modulo ZP. That's obvious. And so, as a result, now let's do it for n finite first. If we look at this exact sequence here, naught goes to En prime, and then, so this is just the same as, if you like, En prime tensored with Z, and then En prime tensored Q prime over Z prime, this sitting inside it, the quotient is En prime tensored with QP mod ZP, because Q prime mod Z is the same as QP mod ZP. So we have this obvious exact sequence here. It's exact because, if you like, it's a free, finitely generated free abelian group. And we have that for every finite n, and then you just take the inductive limit over all n, and so you get now the sequence E infinity prime goes to E infinity prime tensor Q prime, and then the quotient is E infinity prime tensor QP mod ZP. So now let's remember that En prime for every n, every finite n, is the direct summand of E infinity prime. This is one of the things I gave this very simple argument to prove at the end of last lecture. And moreover, that the E infinity prime fixed by gamma n is the same as En prime. This is, of course, true essentially by Galois theory. It's just you remember always that it's obviously the statement for the En prime, and it then follows for the curly En prime because of the cohomology of the units is trivial. So, as a result, it follows from this that E infinity prime tensored Q prime over Z gamma n, because this En prime is a direct summand, will just be En, because of these two facts here, this will be just En prime tensor Z Q prime. All of this is just completely straightforward algebra. So that tells me what the H naught of gamma n acting on E infinity prime is. Now what about the H1 of gamma n acting on E infinity prime tensored Q prime? Well, of course, this is the inductive limit of the H1 of over m greater than or equal to n. This should be Fm over Fn here, and then Em prime tensor Q prime. But you see, now these cohomology groups, these H1s now of a finite group acting on Em prime tensor Q prime, they have to be zero because the whole point is that Em prime tensor Q prime is strictly p divisible. Remember, Q prime are the rational numbers with the power of p in the denominator. So this group is both finite and p divisible, so it must be zero. And of course, then we have that for every n, and so we get that H1, every m rather, and so we get that the H1 of gamma n acting on this group is zero. And so if we now go back and take the gamma n cohomology of this exact sequence here, you see you get, and then you use both these facts here, you see straight away that you end up with the exact sequence. Naught goes to En prime tensor Qp mod Zp. That comes from the gamma n cohomology of this, and I mean of this term here, and then you get E infinity prime tensor Qp mod Zp gamma n, and then that's coming from this term here, and then we go on to the H1 of gamma n acting on E infinity prime coming from this term here, and then of course the next term is zero because of this remark here. Right? So we end up with this exact sequence here, which is the heart of the proof. And we're going to be discussing it in detail now, but the whole point is because of the Dirichlet-Chevalley theorem, we know exactly how big this is, what its divisible subgroup is. And the only question we have to, in some sense, worry about before we get into the details is, what about this group here? How big can it be? It's a priori, it's not obvious that it couldn't have divisible elements. So let me state a proposition, which again is, of course, in Iwasawa, and we'll just assume it now, but then I'll come back and prove it later. It's not quite obvious. So let me write now An prime for the p primary subgroup of the ideal class group of In prime modulo Pn prime. Remember, In prime is the free abelian group on the primes which do not divide P, and Pn prime are the principal ideals in there. So now the claim is that for all n greater than or equal to naught, this H1 of gamma n acting on the unit of E infinity prime is the same as the kernel of An prime to A infinity prime. I mean, that's not obvious. I will prove it later. And by the way, this is here for this isomorphism. It is essential, as we'll see when we come to the argument, that you actually work with the prime ideal class group and the prime unit group. It's false that you don't get an isomorphism if you work with the whole ideal class group and the whole unit group. So it is important we're working with that now to get an isomorphism. So in particular, because AN prime, of course, is a finite group, the conclusion is that H1 of gamma n E infinity prime is always a finite group. So now let's just assume that theorem, and let's now go on and discuss the consequences of this fundamental exact sequence here of Iwasawa's. So as I remarked before, let me write now Sn for the number of primes of Fn above P, and En prime tensor Qp mod Zp by the theorem of Dirichlet and Chevalier. That will just be, we know it's free abelian, free divisible group. I mean, it's a divisible group, Qp mod Zp, to the rank of En prime as a Z module, and that, of course, is R2 times P to the n. That's the R2 of the field Fn, plus the number of primes of Fn above P minus 1. We're simply using the classical theorem about the size of unit groups. Now that, I guess, goes here. So therefore, because this is a finite group, we conclude that if we look at now the object in the center, that its maximal divisible subgroup is Qp mod Zp to this R2 of P to the n, R2 times P to the n plus Sn minus 1. So it's obvious, because assuming our proposition now, because we need the finiteness of that, there's nothing divisible there. So now what we're really interested in, so these are discrete P primary modules, but we now want to pass to the Pontryagin dual of that. So Y infinity is the homomorphisms of E infinity prime tensor Qp mod Zp into Qp mod Zp, so that will be a compact module now. And so by Pontryagin duality, the gamma n invariance of E infinity prime tensor Qp mod Zp, here they will be dual to the gamma n co-invariance of Y infinity prime. That's the whole point, just by Pontryagin duality. And now let's note that Y infinity prime is, of course, a finitely generated Zp module, because we just apply the previous result when n is naught, and we see that its gamma co-invariance is a finitely generated Zp module. So by the usual Nakayama's lemma, that tells me that Y infinity prime is a finitely generated lambda gamma module. And because of this, that we've determined the divisible subgroup here, we've shown that the Zp rank of Y infinity prime gamma n is R2 times P to the n plus Sn minus 1 for all n greater than or equal to naught. Now let's also remember that this totally elementary fact that there exists some integer n naught such that from Fn naught onwards all primes above P are totally ramified in F infinity. This is clear because P is totally ramified in the extension Q of mu P infinity. This is one of the first results we prove about cyclotomic fields. And so when you just translate the thing by a finite extension, you end up with knowing that at least from some point onwards, all primes are totally ramified. The n naught is not terribly, well, it is important if you want to analyze things a little bit more carefully, but and so the consequence of this is that if you take n to be greater than or equal to n naught, then the SNs, they're all equal to Sn naught, which I'm going to call S. Right? That's the consequence of it. And so the conclusion is that we have that y infinity prime gamma n has Zp rank p to the n R2 plus S minus 1 for all n greater than or equal to n naught. That's what we've shown. And therefore, by the structure theory, here we appeal again to this fundamental structure theory, which is carefully stated in my first lecture, even though I didn't have much time to talk about it, that tells us that the lambda gamma rank of y infinity prime is, in fact, equal to R2. It's precisely what comes out of the structure theory. Now, this is not quite the theorem that we want, because we're actually, let's go back to Kummer theory. And let me remind you that we're interested in this field n infinity prime in here, which you get by joining all p power roots of elements of E infinity. But by the way, of course, E infinity prime tensor QP mod ZP is obviously the same as curly E infinity prime tensor QP mod ZP, because you're just dividing out one by a divisible group. And by Kummer theory, the Galois group of n infinity prime over f infinity, that's the one we want to look at, is the homomorphisms from E infinity prime, or either curly or without, tensor QP mod ZP into mu P infinity. And you should bear in mind that for this to be an equality as gamma modules with the natural gamma actions, you have to have gamma, of course, gamma acts on this in the usual way by inner automorphisms. It acts on this in the usual way, and it acts non-trivially on mu P infinity. It acts on mu P infinity by the cyclotomic character. So there is a Tate twist involved here, but in other words, if you think of it in terms of our previous module, y infinity prime, which is just the homomorphism of that into QP mod ZP with trivial action, that in fact the relationship between the two now is that to get, because you've got trivial action here, to get the correct action of the p power roots of unity, you have to tensor this with the Tate module of this Tp of mu is the projective limit of the mu p to the n, and of course this is this is a ZP rank 1, but gamma is acting on it by the cyclotomic character. So it's a Tate twist. And now there's a little, and of course, so now when I write this, let me remind you that gamma is acting on this object on both factors. In other words, sigma of A tensor B is sigma A tensor sigma of B. There really is a twist going on there. But now I leave it to you. This is just a piece of simple, pure algebra that I leave you to think about, that if you have a finitely generated lambda gamma module and you take the Tate twist of it with this twisted action or by TP of mu, or you could take any power, positive or negative of TP of mu, that the twisting does not change the rank, the lambda gamma rank. Of course, it will change the torsion submodule, but we're not interested in the torsion submodule at this point. So therefore, we have shown now, where the conclusion is that theorem B, that we've actually shown that the Galois group of n infinity prime over f infinity has lambda rank equal to R2, which, because the base field F has to be purely imaginary, that's the degree of F over Q divided by 2. Now, in fact, I mean, as I mentioned yesterday, Iwasawa points out that this proof actually tells you more than that the rank, that if you analyze it a tiny bit more carefully, you can actually determine the whole torsion submodule. And it's quite, I mean, I'm not going to write it down explicitly, but and it turns out that it's a free, that there's no, the torsion lambda submodule is a free ZP module. And you actually know what its whole structure is and its characteristic power series. It's a very simple object, so that all the mystery about, and there is a mystery about what happens with the torsion submodule, is going to be tied up with this Galois group of m infinity over n infinity prime. Okay, so now I want to, so this proves theorem B at least, subject to this proposition about the H1s of gamma n E infinity primes being the same as the kernel of A n prime to A infinity prime. So I now want to explain the proof of this statement. It's not very difficult, but I want to go through it. And obviously, to prove that, I mean, we can, of course, the H1 of gamma n, as usual, I can switch between the curly E infinities primes and where the roots of unity have been divided out, and the ones which are the Latin ones where the E infinity primes are there. It makes no difference. So, I can, everything will follow by, if I can prove this statement here. Now I'm going to go back to, this is of course from A n prime to A infinity prime, but I'll actually prove now the proposition for all m greater than or equal to n, from A n prime to A m prime. And I'm going to give the map the other way because it turns out to be the natural thing to actually explain it. And then once we've got this theorem, we just pass to the inductive limit over all m greater than or equal to n, and that will give me the theorem that I want in that case. So let me fix a generator sigma. So, of course, the Galois group of Fm over Fn is a cyclic group of order p to the m minus n. And so let me fix a generator sigma of this Galois group of Fm over Fn. And I'll write OM prime for the ring of p integers of the field Fn. When I put a prime on something, it means I've localized all the primes above p as usual. And so now I take a C in this kernel. of an prime to am prime. So what does that mean in concrete terms? Well, let me take some ideal A which belong in in prime, which belongs to the class of C. And then to say it's in the kernel means that actually when I go up and look at its image, the ideal it generates in OM prime, that's a principal ideal. So that means that AOM prime will be alpha OM prime for some alpha in OM prime. Okay? And now what I do is I take sigma alpha over alpha. That's the whole idea of the proof. And so you see now, if you take sigma alpha over alpha, two things are obvious. Firstly, that the norm of that from Fm down to F, because sigma is a generator for the group, Galois group, the norm from Fm to Fn of epsilon is 1. And also, because A was an ideal of In prime, this tells me that in fact sigma alpha and alpha, that they again, we're only looking at we're forgetting the situation at the primes dividing P, that they must have the same factorization. So in other words, the ratio sigma alpha over alpha will be a unit. It'll be in Em prime. So, and now let me remind you that the cohomology, the H1 of this will be the units of norm 1, right, over the units which obviously have norm 1. So now I'm going to take tau NMC to be the cohomology class of epsilon in the H1. So this is the map. Now, in fact, once we have this map, it's essentially obvious that it's well-defined, it'll be a homomorphism, and it's injective. These follow immediately from the definition, essentially. So that to complete the proof, really the only thing we have to say something about is this: why is it surjective? And this is where we will use, crucially, the fact that we're working with the prime condition. Sorry?
When you say the cohomology class, do you mean of the one procycle given by sigma those two?
No, I'm just identifying the H. Ooh, firstly, that's skew whiff. It's a cyclic group, the Galois group of Fmn over Fn, so I can identify its H1 with the things with norm 1 over the element, the kernel of sigma minus 1. That's all. I'm using this explicit description of the cohomology of a cyclic group. Okay? So let's talk about this surjectivity of this map. So if we take any cohomology class in this H1 of Galois of Fm acting on Em prime, it will be represented by the same description by a theta in Em prime with norm from Fm to Fn of theta equals 1, right? And so I have to see that that is actually coming from one of these classes downstairs. Okay? So the whole point now is we use for Hilbert's theorem 90. We've got for a cyclic extension here. So this epsilon I can certainly write it as a sigma alpha over alpha. Well, sorry, I take an A. I'm sorry, I'm getting mixed up here. So I now take an A in Im prime, which is defined by to be this principal ideal alpha OM prime. And the point is that because of, I claim that A sigma is equal to A, since alpha sigma minus 1 is a unit. That's the point. The ideal A has to be fixed by sigma simply because alpha of sigma minus 1 is a prime unit. Okay? But now I use the fact that because the A is an ideal prime to P, and therefore the only primes that occur in it are unramified in the extension, then it's obvious that the fixed ideals upstairs by this Galois are precisely the ones that come from downstairs. This is all obvious if you think about it. And so that tells me that, in fact, that if I take A to be the image of an ideal B in In prime, then, and we take C to be the class of B, then if you go back and look at it, and you take tau n of this C, we get the class of the theta that we started out with. So this is the proof of surjectivity. Now, it's rather deceptive. This is a very simple proof. There's nothing deep going on here, but it wasn't obvious. Well, I guess it must have been known already, but, well, at least for certain cyclic extensions, that there was this capitulation of ideal classes. But the first real examples up a ZP extension, this was studied by Ralph Greenberg in his Princeton PhD thesis, and I was hoping to see Ralph earlier to get him to remind me. He found some beautiful examples where the base field F is a real quadratic field, and I guess P was 3. Ralph, are you here? Yeah? Do you remember what the simplest numerical, am I right? It was Q equals 2. Sorry? Ah, yeah. So what was it? Is it Q of square root 225, Ralph? Yeah, but the simplest, the real quadratic example, the case of a real quadratic field with the smallest discriminant, which was it? I think it's 2, and his thesis was subsequently published. So I'm sorry, I should have got hold of him earlier and dug out the example, but there's certainly, he gave some beautiful examples where this kernel is non-trivial for the prime 3. Did you do any for the prime 2 also, Ralph? Aha, okay. Well, it actually turns out to be a very intriguing question. This then later led Ralph, I think, and probably already in his thesis, he mentioned that these conjectures about how if you go up a totally real extension, this beautiful conjecture that we have no idea how to prove, that if you take a totally real number field and you take the cyclotomic ZP extension above it, then, in fact, all ideal classes at any level eventually capitulate. That this is one of these mysterious conjectures about modules being, for some reason, much smaller than they should be. And if some of you have some idea of someday of proving it, that would be great progress. But, I mean, in certain cases, for some nice examples, Ralph proved this. Now, my gosh, I've got plenty of time, but I did want to mention one other result, which is Iwasawa proves in his paper, that you see you can look at, you can look at the quotient of the, so let me write, if I have T of this Galois group to be the lambda torsion lambda gamma torsion submodule, and so if I divide out by Galois group of n infinity prime over f infinity by this, then of course by the structure theory that will inject into it, because there's no finite submodule in it, it will inject into lambda gamma to the rank, which is R2, with a possible finite co-kernel. And now this is, in a way, the first example where that finite co-kernel somehow is interesting, because Iwasawa proves in his paper that, in fact, it's that the module is free. In fact, that finite kernel doesn't exist if and only if this H1 of gamma n E infinity prime is 0. In other words, if and only if the ideal class groups inject up. It's a curious statement, and it turns out that the question of whether or not this module is free also arises naturally in the study of the higher K groups of, like the K2 or the higher even K groups of the ring of integers of these fields. Well, if I can tell a little story, that when I first became interested in these things, I thought that Tate had proven an injectivity statement for these K groups going up, and therefore I thought one could prove that the co-kernel was always, that it was actually free always, that this H1 would have to be trivial. And I sent the proof to Iwasawa. This is when I was a postdoc in Cambridge, and in fact it was correct if you accepted what Tate had said. And he pointed out to me that Ralph had found counterexamples. And so then I went back to Tate, and he looked again. He said, sorry, I've made a mistake. It's only injective when you have, in fact, totally real fields for the K2. So everything was clarified in the end. But it's a curious phenomena that this freeness, this is an example where the finite submodule actually somehow enters the Galois cohomology of the K series. Okay, well, that proves theorem B. So in my last lecture tomorrow, I'm going to give Iwasawa's proof of theorem A, which has nothing to do with the cyclotomic ZP extension. It works in complete generality. You see, I mean, there is no field like this. If you take other ZP extensions, there is no field, if you don't have p power roots of unity like E infinity prime in there, you can. So that's why we don't know how to prove the weak Leopold conjecture for these other, for other ZP extensions, even though it must be true, of course. Even the strong Leopold conjecture must always be true, but the question is how to prove it. Now, maybe I can just take 1 minute to say something too, that it turns out that in the analysis, I mean, Iwasawa's proof of it's one of his basic results that we will, in fact, prove in this theorem A, that there's another purely algebraic construction of involving lambda gamma modules, which is important, and I just will mention it now and discuss it a little more tomorrow. So let's let M be a finitely generated torsion lambda gamma module. And Iwasawa has the definition, well, he writes down a definition of what he calls alpha of M, which is the adjoint, what he calls the adjoint of M. And this is a very interesting, I mean, it turns out that it arises naturally in his proof, as we'll see tomorrow. But it's an interesting algebraic idea, and in fact, Iwasawa just gives a computational, he defines this adjoint by a computational procedure which comes out of the actual proof. But I think it's fair to say that it doesn't give any, I mean, well, let me tell you what its properties are, that just to give you some idea, that firstly, that alpha M is pseudo-isomorphic. It's pseudo-isomorphic to M. It's almost the same as M, but alpha M has no non-zero finite submodule. Somehow it's a canonical way of getting rid of the finite submodule in your Iwasawa module. And what else should I say? Well, what I want to say, though, is that in Iwasawa's paper, he just gives a computational method, but there is a conceptual definition of it that I want to mention now, that alpha of M turns out to be the X1 over lambda gamma of M lambda gamma. It has this very nice homological description. Now, I'm not quite sure who first wrote this description down. I have to say that I have two students. It certainly was written down by Bernadette Perrin-Riou, and it's discussed in detail. You see, it's not obvious why this alpha M that I've defined here, conceptually, I mean, with this definition, you can prove all the nice algebraic properties you want rather easily. But it's not obvious why it's the same as Iwasawa's definition, and certainly this was discussed by, so let me, two people who were students of mine in Orsay, Bernadette Perrin-Riou, and her work is certainly published in her, what's really her thesis now, which I have here, which was published in it's a memoir de la Société Mathématique de France. and it's published, it's volume, it's number 17. Volume 114, 112, fascicule 4. Anyway, I don't know if it's possible to get this online. If anyone's interested, I have my own copy here, but she discusses it rather thoroughly because she uses it then in her work on Iwasawa theory of elliptic curves with complex multiplication. But I should say that it was also discovered either simultaneously or perhaps even before that by another student at Orsay called Patrick Billot. And he discussed it in detail in his thesis, and I have to confess I'm not sure if his thesis was ever published. So it may be that the Perrin-Riou account is the only good one in the literature, but it is excellent, but it's due to both of them, and I've forgotten. I have a feeling that they sort of discovered it independently, more or less, at the same time, because they were looking at analogues of Iwasawa's papers for elliptic curves with complex multiplication. Anyway, it turns out that this rather conceptual definition is the same, I have to finish now, as the one that I will write down, we'll see emerge out of the proof tomorrow in Iwasawa's case. But it's an interesting, purely algebraic construction. Thank you.
Any questions?
Comment. Ralph's example was
It was, sorry? 229. I knew it was early 200s. That's right. Yeah. And p equals 3, right?
So square root of 229 and p equals 3 was Ralph's example.
What was one of it? He gave many examples, but this is
That's one of many examples. Other questions? All right, let's thank our speaker again.